Row Matrix Introduction. Hello everyone. Today we are beginning our lesson on matrices. To start, it is important to understand that in the study of matrices, we classify them based on two primary factors: their dimensions, which is the number of rows and columns they possess, and the nature of the elements stored within them. Among the various types of matrices you will encounter, one of the most fundamental and simplest forms is a row matrix. By definition, a matrix is classified as a row matrix if it consists of exactly one row. Now, keep in mind that while the number of rows is strictly fixed at 1, the number of columns is flexible. It can be any positive integer, which we typically denote as n. As we move forward in the next few slides, we will explore how this specific structure defines the order and the general notation of these matrices. Understanding the structure. Now that we have a basic definition of a row matrix from the previous slide, let us dive deeper and break down its structural components to understand exactly how it is constructed. First, let's look at the row. In mathematics, a row refers to the horizontal arrangement of elements. As we established in the introduction, the defining characteristic of a row matrix is that it consists of exactly one such horizontal line. Next, we have the columns. While rows are horizontal, columns are the vertical arrangements. It is important to note that while the row count is fixed at 1, a row matrix can have any number of columns, whether it is 1, 2, 3, or any positive integer n. This brings us to the concept of the order of a matrix. The order is always written as the number of rows multiplied by the number of columns. Because a row matrix always has only one row, its order is expressed as 1 by n. To represent this formally, let us look at the general notation. If we denote a row matrix as capital B, it is represented as B equals B sub ij, with the order 1 by n. Let me explain these indices for you. The letter I represents the row index. In the case of a row matrix, I will always be 1 because there is only one row. The letter J represents the column index, which ranges from 1 up to n. Finally, the term B sub ij represents the specific element located at the ith row and the jth column. Understanding this structure is essential, as it will allow us to apply these concepts to a real-world example in the next slide. Real-world example. Now that we have covered the theoretical definition and the general structure of a row matrix, let us apply these concepts to a real-world scenario to see how they work in practice. Imagine a shopkeeper who wants to record the prices of 3 different items: a pen, a notebook, and an eraser. Instead of listing these prices vertically, the shopkeeper chooses to record them in a single horizontal line. Let us walk through this process in 3 simple steps. First, in step 1, we identify the data. The price of the pen is $10, the price of the notebook is $40, and the price of the eraser is $5. Moving to step 2, we arrange this data into a matrix. By placing these values side by side in a single row, we form matrix P, which contains the elements 10, 40, and 5. Finally, in step 3, we determine the order of the matrix. As we observed, there is only one row and there are 3 columns. Therefore, the order of matrix P is 1 by 3. In this example, matrix P is a row matrix because it consists of exactly one row of data. This practical application reinforces the structural rules we discussed in the previous slides, and it sets the stage for the key takeaways we will summarize in the next section. Key takeaways. First, let's reinforce the definition. A row matrix is simply a matrix that consists of exactly one row. Because the number of rows is always fixed at 1, the order of a row matrix is always expressed as 1 by n, where n represents the number of columns. To visualize this more simply, you can think of a row matrix as a horizontal array of numbers. In terms of general mathematical notation, we represent this as matrix B, which equals a sequence of elements starting from B11, B12, and continuing all the way to B1n. Notice how the first index always remains 1, as we are staying within the first row. Now that we have looked at a practical example with the shopkeeper's price list, let us summarize the key takeaways to ensure you have a solid grasp of the concept. Keep these fundamental points in mind, as they will help you avoid some of the common pitfalls we will discuss in the final slide. Common mistakes to avoid. First, it is very common for beginners to confuse a row matrix with a column matrix. To keep these two distinct, simply remember that a row matrix is horizontal, much like a sentence written across a page. In contrast, a column matrix is vertical, similar to a pillar supporting a building. Second, let's address the order notation. Some students mistakenly write the order as n by 1. However, as we established in our discussion on structure, matrix notation always requires the row count to come first, followed by the column count. Therefore, for a row matrix, the order must always be expressed as 1 by n. Finally, be careful when identifying the index of an element. If we look at the general element b sub ij, remember that the first subscript represents the row. Since a row matrix consists of only one row, that first subscript will always be 1. For instance, you will see elements labeled as b sub 11, b sub 12, and b sub 13. The first digit remains 1 because you are always staying within that single, first row. Now that we have covered the definition and a practical example, let us conclude this lesson by discussing some common mistakes to avoid so that you can be precise in your work.